In today's video, we're going to continue talking about the method of undetermined coefficients. And in particular, we're going to be looking at some of the things that can go wrong when you try and guess a particular solution. For example, let's try to solve the non-homogeneous ODE y double prime plus 2y prime minus 3y equals e to the x. Now I would start this, as always, by trying to find the complementary solution. So let me set the right-hand side equal to 0 and solve that equation. Now I note that this particular equation is homogeneous with constant coefficients. For constant coefficients, we need to guess an exponential function, and that gives us the auxiliary equation y squared plus 2r, this was 3, minus 3 equals 0. So from that we get two solutions corresponding to the two different r values. We get the one solution e to the x, and the other solution y2 equals e to the negative 3x. So my complementary solution will have the form c1 e to the x plus c2 e to the negative 3x. In step 2, we'd like to find a particular solution, y sub p. So I'm going to look to the function on the right-hand side of my differential equation. The function on the right-hand side is exponential, so I'm going to guess a function which is also exponential. Now with y sub p equal to c e to the x, all the derivatives of y sub p are going to be unchanged. So if I plug that into my differential equation, I get c e to the x, and then it was plus 2y prime, and then it was minus 3y, and we need to make that equal to the e to the x on the right-hand side. But if I do that, look what I get on the left-hand side. We get plus c plus 2c minus 3c, which simplifies to 0, and 0 and e to the x can never be equal. So what's the issue here? Why isn't this working this time? The issue is that the guess that I made for a particular solution is exactly the same thing as one of the complementary solutions that I found in step 1. So of course it made the left-hand side equal to 0. Complementary solutions always make the left-hand side equal to 0. But we want the left-hand side to be equal to e to the x, not 0. So what happens if the recommended guess for y sub p turns out to be the same thing as a complementary solution? If your initial guess for y sub p is a complementary solution, then multiply your guess by x. Multiply your guess by x, and then try your guess again to see if you can get it to work. For example, in this exercise, I'm going to guess not yp equals c e to the x. I'm going to reject that guess because that is the same thing as one of our complementary solutions. Instead, I'm going to take my initial stab and multiply that by an x. I'm going to try c times x e to the x. Now with this guess, I'm going to go ahead and use product rule to calculate yp prime and yp double prime. So we have the first times the derivative of the second, plus the second times the derivative of the first, and then again, first times the derivative of the second, plus the second times the derivative of the first. So after a little bit of algebra, we find that y double prime is equal to cx e to the x plus 2c e to the x. So now let's try plugging this into our differential equation to see if we can figure out the value of c. Y double prime plus 2y single prime minus 3y we need that to be equal to e to the x. So let's do some cleaning. We have c times x e to the x plus 2c e to the x plus 2cx e to the x plus 2c e to the x after distributing minus 3cx e to the x, and we need that to be equal to the e to the x on the right side. Now if we combine like terms, we find that the three terms containing x e to the x completely cancel out, and the terms containing just e to the x can be combined into 4c e to the x. Now we have something that we can actually solve for c. If I solve this for c, I find that I have 4c equals 1, so c is equal to 1/4. And therefore my particular solution is equal to 1/4 x e to the x. And once I've found a particular solution and a complementary solution, I can put them together into the general solution. Y is equal to c1 e to the x. Let me scroll all the way back up so I can remember what our complementary solution was. The other one was e to the negative 3x. And then plus the one particular solution that we found. For an even more dramatic example of this phenomenon, let's consider the second differential equation, y double prime minus 2y prime plus y equals e to the x. Let's get the complementary function first. So let's set the differential equation equal to 0. This has constant coefficients, and the only reason that I keep emphasizing that is because I don't want you to get mixed up with the Cauchy-Euler equations that we studied a couple of days ago. I want to emphasize every single time that the reason that I'm making this particular guess is because this is a differential equation with constant coefficients, not a Cauchy-Euler equation. So here is my auxiliary equation, which has a repeated root of r equals 1, e to the x, and x e to the x, and therefore my complementary function is c1 e to the x plus c2 x e to the x. In step 2, we want to find our particular solution, so I'm going to make a guess which is inspired by the function on the right side of my differential equation, in this case e to the x. But if I make the guess that y sub p is equal to a constant times e to the x, I can predict right away that that guess will fail, because e to the x is already a complementary solution. We found it in step number 1. So I'm going to take my initial guess and I'm going to multiply it by x. This gives me cx e to the x. But I can immediately once again predict that this is also going to fail. Why? Because x e to the x is another complementary solution. So what am I going to do? I'm going to multiply by x one more time, and I'm going to guess cx squared e to the x. So with that guess, my yp prime would be the first times the derivative of the second, plus the second times the derivative of the first. And then I would use product rule again, and I would get the first times the derivative of the second, plus the second times the derivative of the first. And then one more time, 2cx e to the x plus 2c e to the x. These two middle terms are identical, they're just written in slightly different orders, so they can be combined. 4x c e to the x. Actually, let me put c first. So let's stick all of this into our differential equation. Here is y double prime minus 2 times y single prime minus 2 times y single prime plus y with no primes, and I need that to be equal to the e to the x on the right side. Now if I take a close look at this expression, I have a positive cx squared, I have a positive cx squared, and I have a negative 2cx squared. So these three terms are going to cancel out. I have a positive 4cx, and I have a negative 2 times positive 2cx, so these terms are also going to cancel out. So the only survivor, really, is the plus 2c e to the x in this last part of the top row. Isn't that amazing? Look how much that cleaned up. So 2c must be equal to 1, c must be equal to 1/2, and therefore my particular solution has the form 1/2 x squared e to the x. Now that I have a complementary solution and my particular solution, I can get my general solution, that y is equal to c1 e to the x plus c2 x e to the x plus 1/2 x squared e to the x. All the solutions to the non-homogeneous ODE must be of this format. That concludes today's material. When you're using method of undetermined coefficients and your guess of a particular solution happens to coincide with one of the complementary solutions that you found in step number 1, take your guess and multiply it by an x. If it still happens to be a complementary solution after doing that, multiply it by an x again. And with this, you can usually eventually stumble across a particular solution. Now, I know this can feel a little bit weird in practice, There's so much of this course is we just figured out a way that usually works, and that's what we do most of the time. And unfortunately, that's the reality of a lot of applied mathematics. If you're interested in things that are more rigorous and logical and feel more stable somehow, applied math is perhaps not for you. You may be more interested in what's called pure mathematics, which is the pursuit of rigorous theorems and really reliable algorithms that work all the time.